The electron energy and position are complementary. We've got kinetic energy. This is the general equation for kinetic energy. It's 1/2 the mass times the velocity squared. So in this electron, in the atom, if it has a given energy, the best we can do is to describe where it is as an orbital. The Bohr model had orbits, which were nice, understandable orbits like the planet's orbit. This orbital, it's got 2 extra letters on the end, a very different animal. It's a probability distribution map showing where the electron is likely to be found. Many of the properties of atoms are related to the energies of the electrons that are in them. Remember that the kinetic energy, 1/2 mv squared. Here's Schrodinger's equation. It allows us to calculate the probability of finding an electron with a particular amount of energy at a particular location. And the way they do this is with wave functions, because the electron acts like a wave. So the wave function describes the wave-like nature of the electron. And when we plot the wave function squared, we get the shape of an orbital. So calculations show that the size, shape, and orientation in space of the orbital are determined by 3 integer terms in that wave function. And these are put in to quantize the energy of the electron, because we know that the electrons can only have particular energies, and we can measure that energy. So these integers are called quantum numbers. There's 4 of them. There's the principal quantum number, which is n. There's the angular momentum quantum number, which is L, which unfortunately, looks a lot like a 1, but it's an L. And then there's the magnetic quantum number, m sub L. And then there's one more, the spin quantum number, m sub s. Not sure where they got those letters, but we have to deal with it. So let's talk about them in order. The principal quantum number. This is an integer that's going to determine the overall size and energy of the orbital. This is corresponding to Bohr's energy levels. So we go back to that and think about the different orbits, 1, 2, 3, and 4. 2 was higher in energy than 1. And so these principal quantum numbers correspond to that. N can be any integer greater than or equal to 1. The higher the n, the higher the energy, the larger the orbital size. For hydrogen, this equation is true. The energy in principal quantum number for the energy level specified by principal quantum number n is minus 2.18 times 10 to the minus 18th joules times 1 over n squared. So as n gets larger, what happens to the energy? It gets bigger because it gets smaller, but it gets less negative. Oh, those fun negatives. The energy is negative because the electron's energy is lowered by its interaction with the nucleus. As n gets larger, the difference between the orbitals gets smaller. So this is negative, and as n increases, it becomes less negative. Yeah, your expression summed it up perfectly, right? So here's a diagram for hydrogen. So here's the first quantum number, quantum level 1. There's the energy. Quantum level 2, 3, and 4. What happens is as n increases, the energy increases, but the distance between the levels becomes smaller. So 5, where would we predict 5 to be? It'd probably be like, getting even closer, right? And then 6. And they're just going to kind of run together after a while, right? Get really, really close together. The angular momentum number determines the shape of the orbital. So n can be 1, 2, 3, 4, etc. L is also an integer, and it can be from 0 to n minus 1. So what would happen if we had, what would happen if we used the program correctly? What if n was 3? Then n minus 1 would be what? 2. And so L then could be 0, 1, or 2. So it starts at 0 and goes up to n minus 1. What if, I'll put this over here on this side. What if n was 0, we'll call that number 7. What if n was 1? What could L be? It could only be 0. So L would be 0. So the value of L designates the shape of the orbital. You guys have at least a vague remembrance of these letters S, P, D, and F? Yeah. So those are the different orbital shapes, right? So L equals 0 corresponds to S. And L equals 1 is P, L equals 2 is D, and L equals 3 is F. The magnetic quantum number specifies the orientation of the orbital. It's the direction in space. So the values here are from minus L to plus L, including 0. So for that p orbital, for p orbitals, what does L equal? One. It went 0, 1, 2, 3, S, P, D, F. So P is L equals 1. So then M sub L is going to be have possible values of minus 1, 0, and plus 1. And that gives us the number of orbitals of that particular shape. The p orbitals, there's 3 of them, and they have there's 3 different orientations. So if L is 2, the values of M sub L are from minus L to plus L, including 0. And so there we get 5. Any questions? How about why? Why do we have to talk about this? Then there's the spin quantum number. This identifies the orientation of the spin. Electrons have spin. They all have the same amount of spin. We just think of the direction of the spin. So you could imagine them like little tops, which they're not, but little tops, some spinning clockwise or counterclockwise. That's the idea here. So MS can either be plus 1/2 or minus 1/2. So the spin can be up or down, we usually say, plus 1/2 or minus 1/2. So we use these quantum numbers to describe an orbital. Each specific combination describes one orbital for n, L, and M sub L. And then if we throw in M sub S, we've described a particular electron's situation. So this example, n equals 1, and L equals 0, and M sub L equals 0, describes the 1s orbital. Orbitals with the same value of n are in the same principal level, or sometimes we call it a principal shell. So this is where thinking about the Bohr model helps a little bit. The shells got bigger. The orbits got bigger as you went out, right? And these principal levels, the orbitals do get bigger as you go out, and they get larger in energy. If we've got orbitals that have the same values of n and L, then those orbitals are said to be in the same sublevel or subshell. So shell and level are 2 terms that we use kind of interchangeably. Pictures, love pictures. It'd be good if I could see the picture. Okay, so what are we looking at here? So here's n equals 1, and the possible values for L are just 0. So there's only one possibility here. And m sub L, remember, was minus L to plus L, including 0. And so there's only one possibility here. And so this is the 1s orbital, and there's just the one orbital. Going up to n equals 2, for L equals 0, that's an s orbital. That's what L equals 0 means. And when L equals 0, m sub L can only equal 0. There's one orbital here. When n equals 2, L can also equal 1. L being equal to 1, we call P, right? Why don't we just call it L equals 1? Well, because that would be too easy. So here we've got the 2p orbitals. When L is 1, m sub L can be minus 1, 0, or plus 1. That's where we get the 3 different orbitals. These guys have the same energy, but there's 3 of them. And we go up to n equals 3, we can get 1 3s orbital, 3 3p's, and 5 3d's because of the possible combinations of the quantum numbers. Does that make any sense at all? This much? Little tiny bit?
Wait, I thought L was like n minus 1.
It can go up to n minus 1. L can be up to, it starts at 0 and goes up to n minus 1. And then m sub L is plus L to minus L, including 0. So in general, the number of sublevels within the level is equal to n. So the first level has 1 sublevel, the second has 2 sublevels, the third has 3 sublevels. The number of orbitals within a sublevel, personally, I don't find this very helpful. 2L plus 1. Yeah, I just don't find that very helpful. And the number of orbitals in a level, I think there's a mistake in the slide. Right, that doesn't make any sense. It's probably supposed to be equals to n squared. I really don't like that slide at all. Let's go on. List the quantum numbers associated with all of the 5D orbitals. Okay, so this will be good. So 5D, what is n? Has to be 5, right? And the D tells us that L equals what? SPD equals 3. L equals 0 is S. L equals 1. I'm sorry. That's number 8. SPD 0, 1, 2. That's okay. I'm sorry too. L equals 2. So that is what 5D tells us. Okay, so then what's the next quantum number? M sub L. What are the possible values for that? It can go from minus L to plus L, right? So minus 2, minus 1, 0, 1, and 2. And then M sub S is actually just about the electron, right? So that doesn't really specify an orbital. That talks about the orientation of the electron, the spin of the electron. So how many 5D orbitals do we have? Well, they all have n equals 5 and L equals 2, right? This is the same for all of them. This is the only one that's different. So how many values are there? 5. So there's 5 of these 5D orbitals. The D orbitals, there's always 5 of them. The P, there's always 3. The 1, there's always, the S, there's always 1. The 1 is always S, something like that. Is this like, I think I can, yes. Your question? Or you just wanted to gaze on its beauty? ML is the angular momentum, and MS is spin. S for spin. It can spin up or spin down. This has to do with the electron itself. This has to do with the different orbitals that can hold the electrons. You had a question, Emily?
How many is in F?
How many in F? Well, that's a good question. 7. So for the F, L equals 3. And so then M sub L equals -3, -2, -1, 0, 1, 2, 3.
So if we were to go a level above that, it'd be 9, right?
Yeah, goes 1, 3, 5. 1, 3, 5, oh, 1, 3, 5, 7, 9. Yeah. It's counting by 2s on odd numbers. MS, each of these would describe an orbital. Each orbital holds 2 electrons. One will have positive spin, one will have negative spin.
And so the orbital, if we were to look at a picture, that's like the different positions, right?
Right. It's easier to talk about the p orbitals, so like 2p. There you'll have m sub L equals -1, 0, and +1. And so you'll have one orbital that's vertical, and one that's horizontal, and then one that's, so if you have Z and X and Y, 3-dimensional space. They're perpendicular to each other in 3-dimensional space. And that's what the M sub L does. It talks about the orientation of them in space.
So for hydrogen,
Mm-hmm.
that only has 1 electron in its 1 orbital, would the spin be negative or positive?
Well, that's a good question. We generally, I believe, say that the spin is positive for the first one and negative for the second one. But with the whole uncertainty principle thing, you can kind of imagine how we can't really measure that. We do know that when there are 2 electrons together in an orbital, they are paired with opposite spins. You don't have 2 with parallel spins. You guys, brains full? Her brain's full. We'll stop for